Okay, so in our last video, we got this general solution. And so next up, I just wanted to go through some examples of what we would do if we had initial conditions that we had to deal with. So first we're going to do it the indefinite way, where we're solving for that unknown constant. Then we'll go through and do it with those definite integrals. So suppose we had the problem of, we wanted to solve that same differential equation, dy dx minus 3y equal to 6, with the initial condition y of 0 equals 3. So in this case, we would sort of, if we were given this problem to start, we would begin by just solving all those same steps we did in the last video. And being at the point where we have the general solution, y equal to minus 2 plus c e to 3x. And then we would go ahead and use our initial condition, where we note that this is our x value and this is our y value, and we just plug it in to the solution we found. So we say, okay, we must have that 3 is equal to minus 2 plus c e to 3 times 0. And e to 0 is 1, so that's just minus 2 plus c. That means that if we wanted to solve for c, it would just be adding this 2 back over to the other side, and we get that c is 3 plus 2, or 5. So the solution to the initial value problem is y is equal to minus 2 plus 5e to 3x. And then you would be done. So dealing with that initial condition unknown constant is just one extra step in the problem. I do want to real quick talk about general solutions versus solutions to initial value problems, and relate it back to what we saw in our section on direction fields, because sometimes people are confused about why sometimes we have general solutions versus initial value problem solutions. So general solutions represent all possible solutions, and in particular, relating that back to direction fields, that's all the possible curves that could be in a direction field. So all those different places you clicked in the dfield software, or all the different places we traced through arrows, those all belong to the family of general solutions, where c can take on any value to match that curve. The solution to an initial value problem is one specific curve that you got when you clicked on the direction field plotter once. And it's the one that you get when you want to start from whatever the initial condition is in the initial value problem. For the one we just did, it would be the 0.03. So hopefully that kind of helps explain why we have these two different types of solutions. In general, if you have initial conditions given in your problem, you should not have constants left over from integration, would be sort of the rule of thumb. So now that we've done the initial value problem one way, I wanted to go ahead and try it out with definite integrals next. So let's just use definite integrals. Oops. To solve the same problem. Sorry about that. And when we're doing this, we have to start from a different point. So we don't want to have that initial condition in our problem. We're actually going to roll back to before we did the integration at all, sort of back at this step. So if we're at the point of having d dx e to minus 3x y dx equals integral we'd like to use our initial condition. And real quick, I want to note that I wrote this a little bit different. This integral can be sometimes confusing for students to remember what values you plug in. So I just rewrote it. You can think about how we would like just cancel out those dx's and it looks the exact same. It's just that this is sometimes a little bit easier for people to remember what exactly they plug in. But it's the same thing we did before, just notated a little bit differently because it makes setting up the bounds, I think, more straightforward. But really, any way you set it up, you should end up in the same place. So in this case, I'm going to go ahead and switch to those placeholder variables. And all my integrals use x's, so I'm actually just going to have that one placeholder variable s. And I'm going to remind myself that y is also a function of x or s. Oops, no x's, only s's. And then to use the definite integral approach, I put my initial conditions on the bottom and the variable I want to go to on top. And I'm using all of these in terms of x. So I only need to plug in that I start from 0 and I go to x. And I start from 0 and I go to x. And then the y value is going to come up in the next step. Just give it a second. So when we evaluate these integrals on the left side, we just get that thing that's inside the brackets, and we evaluate it from s equals 0 up to s equals x. On the right side, which is always a little bit more difficult to integrate in these problems, we get e to minus 3s divided by minus 3 times 6. And we evaluate that from s equals 0 to s equals x. And then I'm going to go ahead and simplify that to minus 2 because I think students tend to find that happier to look at. I don't really care if you simplify or not in your own work. And then we just want to evaluate it at those different bounds. So we start at e to minus 3 plugging in x, and then we subtract e to minus 3 plugging in 0. And I'll go ahead and simplify that later. I don't want to forget that I'm doing minus becomes a positive, which is really easy to skip if you kind of combine steps. And then on the left side, I'm going to also be plugging in x and 0. So it's e to minus 3x, y of x, minus e to minus 3 times 0, y of 0. And this is when we get to use that y of 0 equals 3. Oops, wrong button, I wanted to undo. So this is going to become e to minus 3x times y, minus e to 0 is 1, y of 0 is 3, minus 2 e to minus 3x, minus means plus 2, and then e to 0 again is just 1. And so from here, I just need to solve for y. And that's going to use the exact same algebra steps we used when we solved for y before. So we're going to get 2 plus 3 is 5, minus that 2 e to minus 3x, but then the e to minus 3x sort of cancels that out and becomes e to 3x there. And that's the solution. And it matches the one we had before. So again, you can use either approach, whichever one is better for you is okay. They will end up in the same place.